Hello, everybody. Welcome to today's webinar. It's my pleasure to introduce today's speaker, Liz Munch from Michigan State University. Liz is going to talk about the truncated interleaving distance for Reeb graphs. So please, Liz.
Thank you. Can you hear me okay? I'm hoping this is working out. Fantastic. Yes, so thank you all for the invitation. I'm going to apologize in advance because apparently my internet does cut out sometimes. So if I freeze in a funny position, I'm sorry. I'm also happy to take questions. So please stop me after that and I can repeat whatever it was that I said. Right, so today I'm going to talk about the truncated interleaving distance for Reeb graphs. So this is some recent work with my collaborators, Tim Ophelders and Erin Chambers. Tim is my former postdoc who has since gone back to the Netherlands, and Erin is in CS, professor in CS at St. Louis University. So let's get my page down here. All right, let's see if this works. Yay, okay. Right, so this is kind of my standard opening slide. This is not necessarily the group that I have to sell TDA to, but essentially a lot of what my research is based around is trying to find shape in data. So my group works in a lot of sort of interesting applications everywhere down to the sort of theory that you need to actually do anything with these applications. So we do a lot of stuff involving the shape and structure of plants. So we do plant morphology. We do this with basically studying X-ray CT scans, things that look like this. We do a lot of things with time series. We've done some work with hurricanes, which is kind of a combination of time series and image processing. But the work I'm going to talk about today is going to be related to Reeb graphs. So this guy over here, this is an example of a Reeb graph. And so the idea is, given some sort of function on some sort of data that's got some structure in it, we're going to try to do some sort of skeletonization. So given some input structure, get myself a graph that represents something useful about the original data set. So yeah, so a lot of the stuff that we do, and this is probably how I can sum up almost all of the work that I've been doing in TDA. The general game here is that we've got some sort of input raw data, which again can come in a lot of forms. We are mathematicians, so we can kind of generalize from whatever we've got. We turn it into some sort of topological summary, which in this case is going to be something closer to the graph signature kind of thing. So Reeb and mapper graphs are the best examples of these sorts of things. And then we try to do things like analysis, so statistics, machine learning, and things like that. So one of the big things that you need in order to actually do statistics and machine learning is that you really need to have some notion of a metric, which means that if I have two input objects, some sort of topological signatures, I need to have some way of comparing them, and then I can actually build statistical and machine learning methods to try to analyze them. So in general, the way that I view TDA is the main goals here are to find summaries of the shape of data that basically satisfy lots of properties that we like. So quantifiable, meaning that I can actually make a computer build these things for me without as little user input as possible. Comparable, this is what we're going to talk about today, which is really, I really want metrics. Robust, meaning stability, so noise in my system shouldn't make my summary go haywire. And concise, meaning I'm going to have a lot of input data that's really gigantic. These scans are huge. But if I can replace them with something more simple, like a Reeb graph, then that is incredibly helpful for computation and representation. Right, okay. So let's talk about Reeb graphs, sort of the overview mathematical version of how I tend to think about these things. So given a graph, given a topological space, so in my starting assumption, X is some sort of general topological space, and I have a real valued function. I'm going to start denoting a lot of these things as some form of the space and the function with this comma, just because my notation starts to get lazy. Given a function like this, the Reeb graph is built in the following way. So if I have 2 points in my original base space, let's get blue because that'll be easier. If I have 2 points in my original base space, so say X and Y, I'm going to consider them in the same equivalence class if they're in the same connected component of the same level set. So in this case, my functions, my pictures are all drawn with height functions. So the height, the function value of a point is the height it's drawn in my pictures. This is for pictures and not necessarily required of any of my inputs. Right, okay, so I've built this, this equivalence relation, and so now what I can do is I can look at the quotient space. So the Reeb graph is the space X quotiented out by this equivalence relation with the quotient topology. So what happens here, so all of the points in this particular level set, which looks like probably some sort of disky thing, end up being an equivalence class represented by this point over here. All right. So I am not 100% sure that all the slides have this denoted this way. Depending on my mood, we're going to have R of XF, or just we're going to start messing around with Reeb graphs directly anyway. Right, so the Reeb graph of a nice enough space is a graph, so there is some legitimate reasons for why we get to call these things Reeb graphs. The other perk of these is that a Reeb graph comes with a space and a function. So if you remember, since I'm building equivalence classes off of level sets, every point that's represented in this particular equivalence class has the same function value, and so it makes sense for me to talk about the function value of this equivalence class. It's just whatever the function value was that I got it from. So, okay, sorry, so this is, in this way, so a Reeb graph, I'm always going to think about Reeb graphs as being this pair of data. So it's going to be a graph usually and some function defined on the graph. So I'm going to have a lot of notation that looks like this. Let me just give you my favorite counterexample for this other comment. So the Reeb graph of a nice enough space is a graph. So you can do some weird things and build yourself Reeb graphs that are sort of odd. So this is my favorite example. So if you take a disk and you puncture a hole in it, again, my function is still my height function here. You can sit here and stare at this for a while and convince yourself that this is actually a non-Hausdorff space with 2 points at the origin. Right, so a Reeb graph of a nice enough space is a graph. For nice enough, you can honestly do things like Morse functions on manifolds and all those sorts of things, and you're still going to get a graph. So for the majority of things we're going to deal with, we're going to have nice enough outputs. Right, okay, so for our purposes, for everything that I'm going to talk about here, I'm just going to take as my input data the Reeb graph itself. I'm not going to worry for the majority of this talk about the data, the original topological space that I started with. So when I'm talking about Reeb graphs, I'm just going to treat them as their own objects. So a Reeb graph is a finite graph G with a function which essentially behaves all the properties that we would have gotten if we got this from a, let's say, Morse function on a manifold. So my function is monotone on the edges, meaning that I don't have edges that look like this in terms of my height function drawings. If I had a function that looks like this, I would have just replaced it with a couple of spare vertices in the middle. And then f of v is not equal to f of u for all edges uv. So what I don't want to have are horizontal edges, right? So essentially what I'm implicitly doing here is treating my graph as a topological graph, remembering the function values of all the vertices, and doing linear interpolation of the function value between those vertices. So combinatorially, these things are easy to keep track of. All right, right, so I just need to specify the function on the vertices, and I extend linear to the edges, and then I have all the information I want. Okay, so these things show up a bunch in applications. These are some images from some lovely papers from the Viz community, but these things show up in practice in lots of different places. And so the basic idea with working with Reeb graphs is that they should represent something about the... Oops, sorry? Was there a question? Okay. Please feel free to stop me. If you came in late, I am happy to stop and take questions. And also, if my internet cuts out, please stop me and tell me so I can repeat whatever I just said. Okay, let's see. So these things show up all over the place in applications. And so the game here is that I want to be able to do things like compare two Reeb graphs with some sort of metric to be able to do analysis if, say, I had, I don't know, 100 different parts that look like this, and I wanted to see what the differences were in terms of something with the shape and structure. Okay, so metrics, there's a lot of option for metrics. So in general, when I'm talking about Reeb graph metrics, the important thing that I'm going to point out is when I'm thinking about metrics, these things should have, we would hope, the following properties. So if you give me two Reeb graphs, so again, this is supposed to be all of the data for one Reeb graph and all of the data for another Reeb graph. my distance should be 0 if and only if they're the same. And in my context, the same both means the graph itself is the same and the function defined on that graph is the same. So for the purposes of an example, so I can look at this guy right here. So this is I've basically taken the same underlying space and a slightly different function. Sorry, I haven't been able to line this thing up properly the way I want. But if I change the function over here just a little bit, the Reeb graph I get out changes just a little bit. The underlying graphs are the same, right? So, not that one. The underlying graphs of these two things are the same. The only difference is the function value. And so what that means is that even though the graphs are the same, the distance should not hand me 0. It should hand me something that's got to do with, it's got something to do with how far apart, I guess, this bubble thing has to change. On the other hand, I would also like to be able to compare graphs that are not necessarily homeomorphic, right? So in this case, I should be able to compare a graph. In this case, it's got first Betty number of 2 versus 1. I should still have the ability to compare those sorts of objects. There's a bunch of options for these sorts of things that have come out within the last several years. This is a really fun place to be working right now. So one of the first ones was functional distortion distance. I'm going to talk a lot today about... Oh, can you hear me okay? We good? Cool. Okay. Please feel free to stop me. So we're going to talk mostly about the interleaving distance today, but there's a bunch of other options. There's the functional distortion distance. These are actually very closely related. This is just 2 other papers about the combinatorial edit distance. There's the bottleneck distance for persistence diagrams, where basically you turn your Reeb graph into a persistence diagram and compare them that way. There's lots of these things. They're all very related to each other, which I'm not going to get into today because of time limitations. So there's lots of other things, but we're going to talk about the interleaving distance today. So the goals for this particular talk is we've actually developed a new family of interleaving distances by essentially modifying a little bit of the definition, which makes it interesting. So what we're going to do is build the truncated smoothing operation, which is what I have to modify in order to actually build this metric. And then we can talk about some equivalence of these metrics with other members of the family and some basic properties and things like that. Okay. Everybody doing okay? Questions? I really desperately miss human feedback, so we'll get there eventually. Okay. All right. So let's talk about truncated smoothing first, which shouldn't make any sense to you in terms of anything I've said yet, so let's get there. So the sort of idea of what it is we're messing around with here, we start to get close to sort of the notions from dynamical systems, where I'm going to talk about a continuous flow in the following way. So if you give me a metric space, which in about a half a slide, my metric space is going to be Reeb graphs, and my distance is going to be some distance we're going to talk about in a little while. My flow is going to be a continuous map that basically takes in some sort of one parameter varying thing and spits out from a starting object, spits out an ending object, right? I'm going to write this as f epsilon of x. So this, in just a second, my x is probably going to be a Reeb graph, and this is going to be some modified Reeb graph. So like epsilon modified Reeb graph, right? And it should satisfy some nice properties. So if I plug in 0 for epsilon, nothing should change. And if I essentially flow forward by a and then by b, I should be the same as going forward by a plus b. Come back. Oh, that was everything. Oh, I left space over there. Okay, right. So yeah, a lot of what I would think of with this would be some sort of starting input object and some ending input object, and I get to sort of flow forward in this space. All right, so we're going to define a particular flow on the space of Reeb graphs that has some nice properties. This is called smoothing a Reeb graph. So here's the basic idea. I'm given some input Reeb graph. Implicitly right now, all of my functions again are height valued functions with a map to R. What I'm going to do is I'm going to what's called thicken this Reeb graph. So I'm going to cross my Reeb graph with an interval. So epsilon, remember epsilon was an input parameter. I cross it with an interval. And I'm going to build a new, well, in this case, a topological space with a real valued function. It's not a graph yet. If I draw it like this, all right, so let's take a look what's going on in here. So if this is my point X, the point X cross the interval is drawn vertically for reasons that'll make sense in just a moment. So up here, this is the point X comma epsilon, and down here, this is the point X comma minus epsilon, and this thing is the point X comma 0. So I've got this new topological space, and I can build a function on it by doing my real value function is my f of x, which was my function from my original graph, plus t, which is the value from this interval. So if I draw my pictures this way, my function is still given by height. So for this particular example, f epsilon of x epsilon should be f of x plus epsilon should be, well, whatever this height is, because this thing should be f of x, and this distance is epsilon. Okay, so I have this thing, which is not a Reeb graph, so that doesn't necessarily help me yet, but what I can do is I can take the Reeb graph of this particular object. So by this I mean if you were to look at level sets and quotient the path-connected components of those things. The resulting object, which I'm drawing sort of on top of my shaded version from originally, is this graph, right? So it's got splits that happen at the various locations in where the splits happen in my weird ribbon-looking picture. And so this is the end result of my operation. All right, so I get a Reeb graph, I thicken it, and then I take the Reeb graph of that object, and that gets me a new Reeb graph. This is what I mean by smoothing. So the epsilon smooth Reeb graph, this is everything I just said in pictures, but with diagrams. So the epsilon smooth Reeb graph of this thing is the Reeb graph of G cross epsilon, or G cross my epsilon interval. So that's my thickened Reeb graph. And then my Q is my quotient map over here, and the resulting object over here, this is what I'm calling the epsilon smooth Reeb graph. So what does this thing do to Reeb graphs? All right, so first example. So if you give me a Reeb graph that's a straight line, my straight line ends up essentially just getting stretched. Why? Because when I cross it with an interval, I end up just pulling my image up a little bit higher. And so then I end up with this sort of stretched Reeb graph. So local extrema get extended by epsilon. If I look at up forks, which is any sort of vertex that has this sort of up, up degree more than 1 and down degree 1, up forks go up and down forks go down. So why does that happen? Well, when I cross it with the interval, essentially that fork gets sort of zipped up to this location and gets stretched out. The same thing happens in reverse for the other guy. And then the interesting property that I kind of like out of this is that small loops shrink. Well, loops shrink and small loops disappear. So what happens with my very small loop here? Well, if I cross it with an epsilon that's larger than the height of that loop, I think actually larger than half the height of that loop should work. If you stare at these pictures as long as I have, the level set that you get ends up being connected for every single value of A. And so my resulting Reeb graph is just a straight line. The loops shrink and small loops disappear. Okay. All right, so pluses and minuses of this whole procedure. So one parameter tuning and simplification of small loops. So I think that this has the potential to be used in applications where I might want to sort of denoise some sort of interesting system. I could imagine some sort of Reeb graph that maybe had some bubbles, but there's a global overarching structure that I wanted to keep intact. On the other hand, there's a little bit of a weird property of these things, which is that the height just continues increasing forever. So for every value of epsilon, my height of my Reeb graph, by this I mean the image, the height of the image here, is just going to keep extending and extending and extending. And that somehow seems a little bit odd. It has some, I don't know, it just seems a little bit odd in terms of what we're about to do with it. So we ended up messing around with this idea of truncation. All right, so here's an example of a Reeb graph. I think it kind of looks like a Star Trek pin. I don't know. I've got this Reeb graph, and I can apply my smoothing operation to it. So here's a couple of steps in the smoothing operation. So you can see, for instance, this small bubble goes away. I've got a little tail that appears up here and keeps extending. I've got a tail down here that gets extended. It's actually kind of underneath the other piece. That's a overlap and not a actual crossing intersection. And all right, so if I want to mess around with truncation, essentially what I'm going to do is I'm going to chop off pieces of the stuff that's getting extended. So in this particular example, so I'm going to truncate in this case by a 2 epsilon parameter, which I'll explain in just a second. So if I'm truncating like this, if my truncation parameter is large enough, I actually start shrinking my image. I can choose a truncation parameter so it actually stays the same. There's a bunch of different modified versions of this. This is sort of the goal of what we're about to define is this smoothing truncation procedure. All right, so in order to define truncated smoothing, I need to have a few more definitions to be able to talk about things. So I'm going to call u tau of GF. This is the set of points with no height tau up path. So what do I mean by that? So this is actually, sorry, so delta is currently equal to tau in my picture. The idea here is an up path is any monotone increasing path in terms of the function. The height of it is how far I go, so that's the height of it. So the set of points in here that don't have a length tau up path, that's what I'm calling u delta. So basically anything that gets close to a tail in here. I've got d tau symmetrically for the downset. So this is my downset here. There's some more of my downset over here. The tau truncation is then what happens if I just delete all of that stuff. All right. So in my example here, all of the black portion of this Reeb graph is my tau truncation of my Reeb graph. So please note I haven't smoothed anything. I'm just defining truncation. All right. So if the black region is the tau truncation, the truncated smoothing is what happens when oh, that is backwards. Ooh, I don't like, oop, okay. Massive typos. That's very much wrong, I think. Oh, I don't trust myself right now. I'm pretty sure I actually want that to be T tau S epsilon of GF. Cool. We're going to double check that in a minute. In any case, my truncated smoothing is what happens when I smooth by epsilon and then truncate by tau, I think. Cool. All right. So let's talk about some examples. If I want to define this procedure, so I'm going to do some just truncation without smoothing first. So in this particular example, I have my original input Reeb graph. If I truncate by epsilon here, so you can see the dashed regions are the ones that I'm getting rid of. So in this case, truncating by epsilon doesn't seem to screw up anything too badly. Truncating by 2 epsilon starts getting a little weird. So if I truncate by 2 epsilon, I end up with actually 2 disconnected components. Here's another version of this where I smooth by epsilon first and then truncate. So this is supposed to be S sub epsilon super epsilon. Again, let's all assume that I am doing this correctly. This is going to be fun for later if I've messed this up. Tau epsilon, T epsilon, S epsilon, right? So I'm going to smooth by epsilon and then chop off all of the stuff that's at height epsilon, or that doesn't have a height epsilon up or down path, right? So in this particular case, my smoothing operation takes me from here to the entire background, including the red dashed lines, and then the epsilon truncation chops those off. And you can see that different amounts of smoothing and truncation do sort of different things to this particular example. If I'm working in terms of my more smoothed objects, the truncation doesn't seem to do anything as weird, whereas if I'm working with my original graph, the truncation has the potential to do some very strange things to the topology. Okay, so let's talk about what choices of parameters can protect my graph from doing anything too weird with the topology. All right, so when is S epsilon tau empty? So if you give me a connected graph, the image of GF, all I mean is f of the entire image of G, which is some subset of R. So if its image is denoted by the interval AB, as long as epsilon, oh, that also looks like a typo. Man, we're doing great today. I believe it's tau less than or equal to 2 epsilon. I'm going to double check that before anything gets posted. For tau less than or equal to 2 epsilon, my image, well, it's still non-empty as long as the height of my image is big enough, but it's empty otherwise. So we can draw that in this parameter space diagram. So I've got my epsilon parameter down here and my truncation tau parameter over here. As long as I'm up in this red region, so a point in here is representing S epsilon tau of GF. If I'm up in this red region, I am definitely an empty Reeb graph. If I'm down here, I'm not. And there's a gray region that we just don't necessarily have a whole bunch of information about. Okay, let's talk about some other properties. So when is S epsilon tau connected? So again, if I start with a connected Reeb graph, I want to make sure that this procedure doesn't end up creating that two connected component issue that we had before. So if GF is connected and tau is again in 0 to 2 epsilon, then S epsilon tau is also connected. All right, so what does that mean? Well, that's as long as I'm down here. Oh, okay, this is actually probably better from this slide than the other one. If I'm down in this region below this thing all the way through that line, then I'm connected. Cool. So we at least have inside of this white region a promise that I am not going to end up with an empty Reeb graph and not going to end up with a disconnected Reeb graph if I started with a connected one. Okay, so this is why I was trying to be very careful before about talking about which one comes first, S or T. So S and T do not always commute. So smoothing first versus truncating and truncating versus smoothing. So if I wanted to do something like S epsilon T tau of this particular example, right? What's going on in here? Well, my tau, because basically every point, you need to have every point have at least one of an up path or a down path of height tau, and nobody does. So in this particular example, T tau of GF is empty, and so the smoothing of that thing is also empty. On the other hand, if I do T tau of S epsilon of GF, right, my smoothing will end up getting me, let's see if I can do this on the fly. My smoothing should end up getting me some sort of, I think it's going to end up looking something like this with poor function values. I apologize for that. In any case, it's going to be something that's not empty. The truncation at this point, if it spreads out far enough, isn't going to disconnect anything, as this thing is non-empty. So these things definitely do not always commute. Okay, so let's see. So in order to talk about when they do commute, I need to have another definition of some properties in here. So we're going to call a Reeb graph T-tailed if it has a height T up path at every down fork and a height T down path at every up fork. All right, so what does that mean? That's essentially trying to get rid of these problems. So this is a sort of degenerate up fork, and it doesn't have a down path of height T, and so this particular Reeb graph is not tau-tailed. Right? There's another example of something that's even simpler, right? So this guy is an up fork, also doesn't have a down path of height. Okay, tau is still equal to delta, and so this thing is also not delta-tailed. All right, so we're going to call this thing weakly S-safe if every component has a point with both an up path and a down path of height at least S. So again, that's sort of trying to get rid of some of these weird zigzaggy issues, but you have to have a path that gets all the way to the top and all the way to the bottom. Well, not necessarily all the way top and all the way bottom, but it has every point has a point that's big enough, essentially isn't going to disappear when I start truncating things. And so we're going to call a Reeb graph S-safe if it has both of these properties. All right, so my theorem down here was supposed to show up later. Oops. All right, so the theorem that we have is that if GF is tau-safe, then everything that you want to have commutes, right? So as long as I've got this tau-safe property, essentially truncating doesn't break anything I didn't want it to break, and so smoothing leaves stuff alone, and that was sort of the same as the other option. Yeah, so the perk here is that if I have a non-empty starting Reeb graph, the epsilon smoothed Reeb graph is 2 epsilon tailed and epsilon safe, and so my commutativity theorem applies. Okay. Right, so here's the sort of full version of parameter space as we had studied it. I haven't actually gone through all of these results. This is kind of the main idea of the things that we're interested in. So in particular, down here I've got that we're commutative we're commutative as long as you're below this particular line. Otherwise, I have to make sure that I specify which order I'm going in. I stay connected as long as I'm below this particular line, and then we have these other properties. Okay. All right, so for the sake of time, let's go talk about the interleaving distance now. All right, so we've talked about smoothing operation and the truncated smoothing operation. So now let's talk about the interleaving distance. The basic idea here, and sort of giving a bit more formalism to the stuff I was talking about earlier, is we can talk about the category of Reeb graphs. So what do I mean by that? Categories are just objects and morphisms. So I have Reeb graphs are my objects. Morphisms are going to be these special maps. So I'm going to restrict myself to only allowing maps between the spaces that essentially preserve the underlying function. All right, so if my input data is 2 Reeb graphs, I guess in this case R spaces is another word for more general Reeb graphs, but you can replace that with Reeb graph. So for 2 Reeb graphs, I have a morphism given by this map phi, which is a continuous map defined on the underlying graphs for which this triangle commutes. All right, so translation, what does that mean? If I have a point in my original Reeb graph and I want to define phi, the only places that it can go are points with the same function value in the other Reeb graph. So my options for phi of x in this particular example are the thing on the left here and the thing on the right here, right? So so for example, if I had the point down here, the only place that this particular point can get sent is to that point in the other graph. So those are called function preserving maps, and so those are the only morphisms that are going to be allowed for, I think, the remainder of the talk. All right, so when we do this smoothing operation, we actually get a function preserving map for free. So given my starting input graph, G, for any point in my original graph, it shows up as a point x, 0 in my thickened space, and I can look at the equivalence class of that guy and get a point somewhere over here. It looks like he might be low enough to be down this way. And it has a uniquely defined image under this thickening procedure by essentially just following your nose through the thickening, through the thickened space. So this is a map that we're going to call eta, and it's going to show up in a lot of places in just a second. So we're going to use this to define our interleaving distance. So when are 2 Reeb graphs the same? The idea here is that if I wanted to think about isomorphisms of Reeb graphs, 2 Reeb graphs are isomorphic, if and only if their distance is 0, and that means essentially that I can get function-preserving maps forward and back that commute with each other in all the sort of standard ways that you would want them to. So we're going to try to use this to give a definition of essentially almost the same. So if I wanted to say that they were, say, at distance epsilon of each other, I could try to build the following generalization of this diagram over here. So I've got 2 input Reeb graphs. I have my eta maps and some smoothed operations, right? So I can take my Reeb graph and smooth it by epsilon and then smooth it again. I can take my other Reeb graph and smooth it and then smooth it again. And I can go looking for a pair of maps that go across and back where essentially they should commute with each other, but it doesn't actually make any sense anymore, to commute with each other. They have to go back in a way that makes these giant triangles commute. So if you trust me on the category theory, I get all of these maps for free by finding these 2 maps. And so this comes down to finding a pair of maps that make something like this commute. So the idea here is that an interleaving is any diagram like this that I can actually make that work. So here's an example where I've got 2 starting input graphs. So in this particular input, I'm going to assume that these are actually at the same, centered at the same place. I'm just drawing the pictures in different locations to be able to compare them. Right, so what happens here? Well, so if I wanted to try to understand something about this particular diagram, right, where can my maps go? Well, the image of this line right here is just kind of stays here for the entirety of the interleaving. So the only choices I get are, what is my map phi here to make this thing commute? Well, now I get to have a choice of how my map goes. Either it's going to go to the left or to the right. For, it's symmetric, it doesn't matter which one I pick right now. So if I watch, it goes around the left. If I look at the image of any point in here, it goes to a point on my Reeb graph over here. Everything in here went to the same place. I only have one option because of the function value limitations. So this triangle automatically commutes for me, no problems. All right, so that's not an issue. However, if I try to find a map over here that makes everything commute, I'm going to break stuff. So here's my original input Reeb graph. Every point only has one location of where to get sent to. So the image gets sort of squashed onto this line. And so what ends up happening is the decision I made of going to the left over here, this map ends up sending everything in the line to the map over here also on the left. So what ends up happening? Well, if I'm a point, let's see if I can get another color here. If I'm a point X and my image going along the top is staying on the left, my image going along the bottom also stays on the left. So that's actually fine. The issue arises if I'm a point on the right. My point on the right lands in the same place. However, if I go along the bottom, I end up on this side. If I go along the top, I stay on the right. So basically, this diagram does not commute. And there's no way for me to build one that does commute. Right? And so what ends up happening here is that I can't actually build an interleaving using this particular epsilon value. However, if I make my epsilon a little bit bigger, in particular larger than h/4 for the height of this particular loop, what ends up happening here is that I collapse out all those problems that were causing non-commutativity, and if you chase this thing around, this one does commute. Basically, for whichever choice you make, it'll still commute. All right, so this is how we're going to build an interleaving out of this concept. So I have two input Reeb graphs. An epsilon interleaving consists of two morphisms, phi and psi, that goes between these things, where I'm going to force a diagram like this to commute. If I can find a diagram like this that commutes, my interleaving distance is the infimum overall possible epsilons for which I can find a diagram that actually makes this thing commute. Okay. That's interleaving distance really fast. How am I doing on time? Ooh, a little rough. Okay. All right, so this has some nice properties that I'm going to make use of in a moment. The interleaving distance is an extended metric, meaning that it is the extended part means that it can take infinite values, but it only takes them if you have different numbers of connected components on your original starting graphs. It is stable in the sense that if you give me two input, that should probably not be a G, that should be an X. If you give me two input functions on the same starting data, I guess it could be a G, it doesn't matter. If you give me two input functions on the same starting underlying space, if I take the interleaving distance between those two, the Reeb graphs of those two things, it's upper bounded by the L infinity distance of the original functions. So, all right. So let's use this whole party to build a new version of an interleaving. So to do this, I'm going to have to generalize my concept here just a little bit. So we can come up with an idea called a categorical flow. So if category theory isn't your thing, you can mostly just replace this notion with a regular continuous flow, but I have to play nice with some of these maps I've started defining. So if you give me the poset category of positive real numbers, a categorical flow is a functor from the poset category of the real numbers to endomorphisms on C. So essentially what's going on here is T epsilon is a functor that goes from C to itself. That basically preserves all the properties that you kind of wanted to have before in terms of my regular flow. So again, what's being sort of hidden in this word functor is that I have to play nice with the maps. Well, really the morphisms. But everything else is just a generalization of this idea of a flow. Okay, So we have this nice theorem that any categorical flow gives rise to an extended pseudometric on the objects of the category. What does that mean? It means that I can get a metric. As soon as I give you a flow like this, I can get an extended pseudometric where the extended is that it could potentially be infinite, but hopefully not when we don't want it to be. And the pseudo is really, this is all up to isomorphisms. Okay. All right, so given a categorical flow, I can give you a new interleaving type of distance. And so what we can do is we can check to make sure that our truncated interleaving procedure is actually also a categorical flow. So my original map eta, so this was this one that basically took points in here, sent them to x comma 0 in my thickened space, and then looked at where they went under the image. So this is x, under the quotient, sorry, the image of the quotient map. Essentially what we can do is we can use this eta to build a whole bunch of other maps that we need to be able to build our categorical flow for the other stuff. The problem is essentially the immediate way that you would think about it, they go the wrong way. All right, so I'm building a few additional theorems into this slide without really saying it. The first one is that I originally told you things about eta going from some Reeb graph G to the smoothing of G. However, you essentially have a notion of eta that goes from S epsilon tau to S epsilon tau plus tau prime, I guess, in this direction, or so S epsilon, oh, I said those backwards, whatever, the one that makes this line horizontal. I get an eta that works for all of these options. So in my particular picture over here, these Reeb graphs are the smooth truncated options for my Reeb graph over here for a bunch of different choices of parameters lined up in the same way as this thing, right? So I have eta maps that go this way. On the other hand, I have inclusion maps that go in the opposite direction. So if I have the truncation of, if I have the truncation, which is the top parameter, if I have the truncation of a Reeb graph, I cut out pieces and so I get an automatic inclusion. So that's what this new map is. Omega is just what happens if I compose those two, so I can start talking about them easier this way. All right. What I want to do is I want to come up with some sort of flow, which really means going forward, and so I kind of need these maps to go up and right in a general sense. So it turns out that we can get the up and right map from my eta map sometimes. How do I do that? Well, if I've got a S epsilon 1 tau 1 and S epsilon 2 tau 2, which in this particular example, let's say it's, this is epsilon 1, epsilon 2, this is tau 1, this is, let's all pretend that those lines are straight, tau 2. My row map, which is, I'm currently talking about this guy on the bottom, my row map here is the restriction of eta, which is the map that would have gone across from the S epsilon smooth to the epsilon 2 smooth graphs, restricted to what happens if I essentially look backwards by tau. So this would be S epsilon 1 minus tau 1 of G. And look at the image basically following your nose along those maps. So what I'm going to end up having to do is restricting myself to the case, if you chase these inequalities around, I need to have I need to be below the line tau equals epsilon, otherwise this backwards smoothing thing doesn't actually make sense. Okay, so this is actually very helpful. So now I have these maps that essentially go up and right, and the rule here ends up being up and right. I have a map row if in my pictures my slope is less than or equal to 1. Slope, there we go. Okay. All right, so I get these up and right maps. All right, so this was, here's the kicker. All right, this was the point. If I give you any slope m between 0 and 1, I get all of these row maps that go up and right. It turns out that this procedure of, I'm going to do SM, this is going to be for a given Reeb graph. If you apply SM, it basically moves you forward by epsilon on the line. This is epsilon. I am teaching calculus. I swear I can remember how to do lines. This is what happens. SM of G is the epsilon, moving forward by epsilon on this line, smooth truncated Reeb graph. Turns out that if you give me any m between 0 and 1 inclusive, this map is a functor that defines a categorical flow on Reeb. And the perk here from our other infrastructure that we built up is that as soon as I give you a categorical flow, I get an interleaving distance. So we're going to call this d sub I m. So m is anything in between 0 and 1. And I get a new interleaving distance for each of these options. Right, so for any slope essentially that shows up in this white region, I get a new interleaving distance. All right, so let's talk about some properties of these things. If you give me any pair of m and m prime with a certain thing I'm going to talk about in just a second, the metrics dim and dim prime are equivalent. Specifically, so the definition of equivalent metrics is that I can find you constants that essentially make these inequalities happen. I don't think there's nothing particularly insightful from the constants themselves right now, other than the fact that they're only based on your choices of m and m prime. One other thing I'd like to point out that I think I missed before, if I make m equal to 0, m equal to 0 ends up being a line with slope 0, ends up being just this straight bit on the bottom. M equals 0 means I have my original interleaving distance. So this definition generalizes the original interleaving distance to this family of distances, right? So so these metrics are all strongly equivalent to each other, with the exception of being equal to 1. We'll talk about equal to 1 in a moment. The basic proof here, once you have the setup, the idea is that I want to have, if I have an epsilon interleaving with respect to one of them, so dim, what I'm going to do is I'm going to go try to build a delta interleaving for the other, which essentially comes down to chasing around maps like this, respecting our slope requirements. So in this case, I'm trying to essentially get across and back between these lines. So from the m line to the m prime line and back. This picture might be the other version, I'm not sure. Essentially across and back in a way that still has all of the maps I need. So where these constants come from is essentially drawing pictures like this and then trying to line up my slopes in a way that makes sense. As soon as you have this strong equivalence, the next question is going to be, how do I deal with that restriction on m, or on m and m prime? So in this example right here, or in this theorem, sorry, my rule here is that the difference between m prime and m has to be less than or equal to 1 minus m prime. So I think better on unit intervals. 0, 1, m has to be less than m prime. Whatever this distance is has to be smaller than whatever this distance is. All right, so in particular, if you want to start talking about, say, comparing things with the 0, the traditional interleaving distance, if m is equal to 0, this theorem only applies to 0 less than or equal to m prime less than or equal to 1 minus m prime, and you end up with something like m prime has to be less than or equal to a half. Okay, so I really want to be able to compare all of these. So we can easily get rid of the restrictions on m and m prime. It turns out that if you chase around a parameter space enough, excuse me, if you chase around a parameter space enough, you can essentially just apply the strong equivalence theorem a bunch of times. You get massively nastier constants, but you still get strong equivalence, so that's useful. Some other properties, all of these things are essentially corollaries of that strong equivalence, and then using all of the proofs of the properties on the original interleaving distance. So if you give me an m between 0 and 1, not including 1, if I have two input functions on the same starting space and I compute their Reeb graphs, I have a stability theorem. If I've got two Reeb graphs with the same number of connected components, then I'm going to have the interleaving distance, the truncated interleaving distance will still be finite. And the truncated interleaving distance is strongly equivalent to the other Reeb graph distances for which we have strong equivalence results with the original interleaving distance. Okay, a few more things, and then hopefully we'll still have time for questions. Okay, let me talk about the obnoxious case of m equals 1. If m is equal to 1, essentially what's going on here is one way that I think about this is essentially something like speed of the truncation. M equals 1 means that if you follow your nose around the extrema don't move, right? So what ends up happening here? If I have two Reeb graphs I want to compare, let's say this one, and they have different images, the smoothing of each of these actually is going to end up being constant. They're not going to move anywhere, and there's no way for me to get a map from one to the other, in particular because, say, this point down here has no point on the other Reeb graph for it to map to. So it turns out that this thing is finite if and only if the images themselves are equal. All right, so the case m equals 1 is a little bit odd. All right, not doing too bad. All right, so what did we do? So the whole idea here was that we defined a smoothing operation s epsilon tau on the Reeb graphs and modified this into a truncated version, which for certain parameters does still maintain some of the topological properties that we want. We show that this thing is a categorical flow, which gives me access to a family of interleaving distance. Distance is a choice of one for every m. And with the exception of the m equals 1 problem, they're all strongly equivalent to each other. Okay, right. So there's a bunch of things that we want to do with this. Let me make one side comment. So we actually found this definition via some things we were doing in terms of Reeb graph planarity. So a Reeb graph is planar if you can draw it in the plane in such a way that it doesn't intersect itself. Actually, this is a bad example. That one is planar because I could have done it somewhere else.
The L1 to 2, it says possible extrusion.
Oh, is that a question? Sorry. Okay. If you have a question, please feel free to stop me. I'm sorry. Right, so we came at this from Reeb graph planarity, which is basically whether or not you can draw a Reeb graph in a way that it's planar and also preserves the function value information. It turns out that regular smoothing doesn't preserve planarity. But truncated smoothing does. So that's the next paper we're working on at the moment. I'm hoping that some of these things will be potentially useful for computation and or applications, just because it seems like there's some nice properties in terms of not stretching out to infinity that can be utilized for any options for approximation computations and for any sort of smoothing in applications where you're trying to use it for denoising. And it also gives me just more options for comparing Reeb graph metrics. So there's a lot of interest in showing when these different Reeb graph metrics are strongly equivalent to each other and different sorts of relations between them. And so this gives another family of options that we can look at for ways of getting some comparisons. Okay. I think that's all I've got. So I should point out thank you to my collaborators, Erin and Tim. The paper that is related to all of this stuff is now up on the archive. And I have a bunch of wonderful students and postdocs who work with me at Michigan State. And thank you, of course, to the NSF for funding all of this. And I would be happy to take questions if you have them. Oh, you might be muted.
Nessa? Hello, Nessa?
Oh, I'm sorry. I put on my camera, but not my microphone. So thanks very much, Liz. This was a very interesting talk, and thank you. So do we have any questions, please? So I have a couple of questions. Just now, so first of all, my question is, are they Reeb graphs or Reeb graphs?
Yes, it's probably Reeb. If you are properly French, it is probably Reeb.
Okay, well, this is
I've never been able to get into that habit. I probably should, and I haven't been able to get into that habit.
Okay, well, don't worry. It was just a question because I was living in the belief that they're Reeb graphs, so I just wanted to make sure if that's true.
Yep. Yes, those are the same things.
Okay. So the next question is this: you said that smoothing doesn't preserve planarity, but truncated smoothing does.
Yes.
Well, if you take truncated smoothing with the parameter equal to 0, isn't that just smoothing? So there should be some conditions.
Oh, yes, sorry, there are some conditions on that theorem that I'm not putting in here. Let me attempt to remember that
for
properly.
Certain values of tau.
Yes, I believe this is the case as long as you have tau between, I don't remember if it's inclusive. I think it's from epsilon to 2 epsilon. I'm not convinced about whether or not the epsilon is included or not, but I know if you're strictly greater than epsilon, you're okay.
Okay, so I thought something like that should be true, probably.
Excellent question.
And then my next question is, so you have this many ways of comparing Reeb graphs, many metrics on them. So could you say something about which distance is useful for what kind of applications, what kind of tasks what would you choose if you have a specific?
That is the $1 million question, which I think is fabulous. Let me go see if I can find my list of, sorry for making everybody go a little crazy. So there's some interesting properties and relations. They all tend to run into the whole computational complex. Oh, no. Where did I not? I just lost it. Sorry, give me a second. I don't know why it jumped down again. Here we go. So computational complexity is an issue with basically all of them, with one exception. Anytime you start trying to directly compare graphs, you're going to run into some computational issues. The exception to that is the bottleneck distance, which is basically in polynomial time, you can turn your persistence diagram into an extended, you can turn your Reeb graph into an extended persistence diagram, and you compare those in with bottleneck distance. That is entirely in polynomial time. The trade-off you get is that you can have 2 Reeb graphs with the same extended persistence diagram, and so you lose your assumption that you're non-isomorphic. You have non-isomorphic Reeb graphs for which the extended persistence diagrams are the same, so the bottleneck distance is the same, so it's not quite as discriminative. There's some really nice by Matthew and Steve that's essentially doing some nice things with like local information and intrinsic metrics and things like that related to this. So it's a mild oversimplification, but yeah, that's the trade-off there. So for computation, this is one of the best places to start, just because this is the one where we actually have, I can like type this into my computer right now and compute it. The rest of them, we're still having issues in terms of trying to figure out ways to approximate or get anywhere with it. There's some very interesting properties in terms of the combinatorial edit distance. In particular, there's a recent paper by Uli and Sausage where they were they're showing universality. So universality of a metric is that whatever metric you're interested in between your Reeb graphs should be stable, so less than or equal to the difference between the input data. Sorry, this is terribly explained. So these are stable, and the universal metric is the largest such of all of these options. So if you have my universal metric is itself has to be stable and is an upper bound for any other possible stable metric, then it's called universal. And so they showed that the combinatorial edit distance is universal. So ours doesn't exactly fit into this framework because while the interleaving distance is stable in the official sense, the truncated interleaving distance is stable with a constant. So ours actually satisfies, let's say, Ti of GH is less than or equal to some constant out here that I have some control on based on the M, but it's not stable in the original definition. So I haven't quite figured out how to fit that into their framework yet. So yeah, so it really, at this point, it kind of depends on the application. There's some other interesting restrictions if you like restrict your Reeb graph to nicer things, but yeah. Sorry, that was a long-winded answer to a good question.
Okay, well, thanks a lot. Very interesting.
Yeah.
Do we have any more questions?
Nessa, you have a question in the chat. You want
Where
to
do I see the? How do I see the chat? I can't find the chat.
It out for you.
Nessa can read it to you.
Yeah.
Okay, so the question is this. About the non-commutativity of S and T, can it measure some property of the Reeb graph? Some like the Lie bracket?
Possibly. So my guess is that anything like that would be related to these tau safe and tau tailed and all of these properties. We haven't thought about that. That's an interesting way of looking at it. I'm not sure. But yeah, I think that's where I would look to see if there was some useful properties in there.
Okay, so thanks very much.
Thank you, guys.
Any more questions? Nothing in the chat.
I have a question, Liz. This is not a really question. It's something like this. Would you please put us your slide where you are talking about the space G cross minus epsilon epsilon FE?
Boop, 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 boop. This guy?
That one.
Yeah.
Yeah. What you, I think if I am understanding well, what you are doing is you are associating to this, I will call it space.
Mm-hmm.
You are associating a graph, okay? A nice graph. That's what you are doing, no?
After this, yeah.
Yeah.
Right. So maybe the better. Let me get the triangle version of the picture. Right. So I don't have it there. Hold on.
Right.
Yes.
Yeah. But no. But I like better the picture, please.
Okay.
Picture. Okay. But you know, this is my question. Do you think that you can develop the theory using your left space? Because I mean, this is going to be a space.
This thing entirely.
Right. Because you know what's happening is that in your left side, look, you are having what we call a two-stratified.
Yeah.
On your left side, you are having
that's exactly what it is. Yes.
Then this is just my very general question. Do you think that you can develop some kind of theory, but using the whole left space? That would be my question.
I think so. I'm trying to remember if so Anastasio. Okay, so let me put some stuff up here. So Anastasios Stefanou. So he was my student from my previous position. He's now a postdoc at Ohio State. So he did this really lovely thesis where he developed this whole category with a flow idea. So everything in here that's sort of, I'm doing like a nicer like special case version of it, but he basically took this and ran with it, where if you have categories with this particular structure.
Liz?
I think the internet is having.
You can.
Okay.
It is.
Sorry.
Can you hear me again? Am I back?
Yep.
Yes.
Okay. Sorry. I told you it was going to happen. Right. So Anastasios did this lovely thesis where he developed this whole idea with categories with a flow, and how you could basically build a metric as soon as you had the sort of starting input. He showed that this construction, you can get a bunch of different sort of standard metrics. I don't think we looked at it specifically for two stratifolds, but in general, he was able to show a lot of really nice properties, including if you swap out the right category and the right flow, you can get things like the Hausdorff distance. You can get variants of the L-infinity distance. You can sort of create this theory that just automatically gets you stability theorems very nicely. It's very lovely. So the answer is, yeah, you could definitely write some sort of interleaving distance on your particular favorite objects with functions, with morphisms. And as long as you have that structure, his thesis gives you this like giant hammer that you can just create a metric and not have to check all of the things that would be an absolute pain to try to check.
Great, thank you.
So thanks very much again, Liz.
Thanks.
If we have no more questions. Oh, there's maybe one more. No, just thank you for the first question.
Thank you.
You're welcome.
Bravo.